today. He's a world-leading expert in algorithms and optimization, especially in the area of hashing algorithms. He's going to tell us about the power of theory in the practice of hashing.
Okay, so I'm happy to be here. I'm always happy to show the logo. Oh, this thing doesn't work. Okay, but I'm always happy to show the logo for our new research center in Copenhagen. So, BARC is an acronym, and it sounds like what a dog sounds like. So it's no other relation to dogs, but we try to draw it so it looks pretty clever and obnoxious at the same time. So I'm going to talk about things which have been both sort of in theory conferences, but also more applied conferences. I think it's very important when you actually do something that could be used for applied work to actually test it and see how much it helps. And I'm quite excited about some of the things that came out of it. So the generic target for me for the last, I guess, 15 years or something like that has been to find simple and reliable pseudo-random hashing. So we want some hash function that we can actually implement, not something from Dr. Thorup's journals, but something that actually has some of the algorithmically important guarantees. So the simplest example of that is low collision probability that Carter and Wakeman pointed out that that's all you need for a simple hash table with chaining. And even though we can't have fully random hashing, getting low collision probability rigorously and mathematically is very easy to get. So again, if we can do that, then we will make some of all the theory that assumes true random hashing works. And I think this is a very critical juncture we're at because randomized algorithms are very popular. There's books about them. They are very simple, very tempting to implement, and often they shove under the carpet how are you actually going to implement the randomness, how are you going to implement the hash functions. And there are plenty of scandals where people have used bad hash functions and then you can't trust the statistics, you can't trust anything you're doing. You're basically just having an average case algorithm. And this is particularly nasty because most of these things work extremely well if you give them random inputs. So if you try to run a random test, if your test is random enough, everything will be perfect. And many of the problems are not even reproducible. Your problems may be that errors happen with a way too high probability. And then they may be very large, so it may be a heavy tail distribution. We're going to talk about things where with probability 1 in X, the things are X times as bad as they should be. But that still means you try to see what's the problem in my code, you run 10 experiments, you may not see any problems. Because it's only sometimes the whole system breaks down. Okay. So the running example I'm going to talk about here is the Jaccard similarity, which is the size of, we're looking at two sets, we want to see how similar they are, and we look at, the measure is just the size of the intersection divided by the size of the union. We could have looked at many other things, but that's just to say this is what we look at in this talk. And the generic goal is to construct the smallest sketch of each set so that when you have to compare two sketches, two sets, you only have to look at the sketches and nothing else. Okay, so you can have a distributed situation where each guy has a huge data set. They just make the little sketches, and to find out how similar they are, they only have to look at those two sketches. They don't have to communicate the whole set. They can forget about it. And so this is a natural front-end bottleneck proposed in big data. This is particularly convincing when you talk to people who don't know what big data is, because of course, what do you want to do with big data? You want to make them small, then they're not big and the problem is solved. I know there's more to big data than that, but let's just keep it simple. And the critical point here is that hashing is used to create the sketches. Somehow you have to create these sketches in a coordinated way, otherwise it doesn't make any sense to compare them. And what I'm going to study here's how different hash function implementation impacts the quality of these sketches. So you have a mathematical description of how to make the sketches, assuming true randomness, and then we're going to plug in different hash functions. So again, we take this Jaccard similarity, and we, for now, do the nice abstract mathematical assumption that we have a perfect hash function, and we're even so lucky we have no collisions. Forget about that. It's injective. You can think of it as a permutation. And let me just get this hand somewhere else outside. Okay. It's almost more annoying, but anyhow. So we look at some element x from the union that minimizes this hash function. When x is uniform in the union, then the probability that it is in the intersection is exactly the Jaccard similarity, because it's just a uniform element, right? And also what we have is that x is an intersection if and only if both sets have the same smallest hash value. Because if the smallest hash value was in only one of the sets, then that set would have had a smaller hash value. Okay, so this is sort of the basic observations that Broder used. So this means that we have this simple thing that the Jaccard similarity is exactly the probability that the two sets have the same smallest hash value. So that's our first sketch, just the smallest hash function. And of course, on its own, it's not worth a lot, but if we want to have concentration and stuff like that, we just repeat this experiment k times with k different hash functions, and then we can do this comparison for each of them. Right, we just look at the number of matches we get and divide by that by k, where k is the number of hash functions used. Okay. And what I just want to note here is that the expected relative error or standard deviation of this relative standard deviation is 1 divided by the expected number, the square root of the expected number of matches, just the standard normal distribution thing. Okay, so now comes this issue which is recurring in this talk. We don't have truly random hash functions. And that typically leads to bias. We say a hash function is epsilon minwise if for every set and element in the set, the probability that that element is smallest is 1 plus minus epsilon divided by the set size. So this is what we talked about before. We said that the smallest element in a set was uniformly distributed, and that's why we could conclude that the smallest element from the union, the probability that was in this section, was the Jaccard similarity. So that was a critical property. But the problem is just that getting bias epsilon requires independence log 1 over epsilon. I don't know. So independence is just the number of elements we can claim. So we say a hash function has independence k if given any k keys, they map independently of each other. Okay, so two independence is the thing we have most of the time. High independence is hard to get by. And the point is just that we actually, if we want to have a subconstant bias, then we need superconstant independence. So typically we get independence by using a corresponding degree k polynomial, or in fact, degree k minus 1 polynomial.
Sorry, k independence is the same as being originated from k random bits?
Sorry?
K independence is the same from coming from k truly random bits?
Well, I mean, there's more to it. So again, typically I'm talking about keys as being just integers. I think it was 64-bit integers. So actually to get independence k, then you would actually need k times the number of k random integers as minimum to get, so not just k bits, but k random integers. Yes, and you get that using polynomials, but the problem with polynomials is they're slow to compute. Well, we'll get back to that, but basically the problem with polynomial is that, okay, so we have minimized the random seed, but to compute any value, you have to visit every coefficient. And as that gets larger, then this is not a very efficient solution. And you're forced to do that. It's easy to do. There are actually very cool results about that, but we'll get back to some of that. We'll get to it. And so, of course, if you have bias, then it doesn't help with all the repetitions. And does it matter in practice? There's a very nice paper of Mittenmark and Vadan that put a lot of theoreticians at ease, which said if you have input with enough entropy, then two independents work as good as random in almost all contexts. Does that mean it works in practice? Well, so I actually ran this thing on, instead of using, it was more natural to look at dissimilarity instead of similarity, which is just how much things differ. And this is just running with bigger and bigger number of samples. So we get more and more concentration. And there's only one problem, the concentration is around the wrong value. But otherwise it looks very convincing, right? So people who got these data out would say, well, the machine clearly agrees it's here. The answer is it's just wrong because of bias. Nobody can do anything about bias. And just to read what you can't read, or maybe some of you can read, this is the top 90% fractile, this is the bottom 90% fractile, and this is just one trace. Okay. So just to kind of indicate it makes sense. And the interesting thing here is that this is a very natural data set, because I look at the dissimilarity between two sets where the intersection was just a bunch of small numbers, then set of small numbers, and the outliers, the differences were random numbers. So you think of, say, coding text, you'll typically use small numbers for common words, and these are exactly the words that you expect to find in many sets. So intersection is mostly dominated by all these small common words, whereas the outliers are those which are random. And in those situations, this measure, you get this large bias. And it's not even required that the small numbers are very dense. You can just take every other or a random subset, because it still only gives a bit of entropy for each number. But for this kind of result to work, you need to have all the bits to have randomness in them, not just one. Okay, so, but just to say, this is a very natural instance that you do appear. When you start looking for it in real data set, you'll see it everywhere. You just need to know what you're looking for. And that's exactly the thing that hits you. Everything can look convincing, and it will work for loads of real data. But then you may discover you're in a situation where you're up against Huffman coding or something like that, and then the thing breaks down because you use the wrong hash function. Okay, so now let's look at a different generalization of exactly the same idea. So we only use one hash function, and we just keep the k smallest guys with that hash function. So instead of using k hash function and using the smallest guy from each, we just use one hash function. So it's really very simple. It's simpler than what we did before. And it's more convenient to just talk about subset estimation. So, of course, the intersection is the subset of the union. Mathematically, we can kind of forget that it was two different sets. We'll just say we have some subset X and we have some subset. We have a set X, we have a subset Y, and we want to estimate the frequency of the subset. And what is that then? That's just the number of sampled elements from the subset divided by K, by the number of samples. Okay, same as before. And I claim this is a good sketch, but you have to think a little bit about it. So if you have two sets A and B, and we've stored the k smallest elements from each of them, then we can create the sketch of the union just by uniting the two sketches and picking out the k smallest elements. But we had to do something. It's not similar. This is no longer linear sketching or something like it. It's a little peculiar what's going on. But when first we have the sketch of the union, then we have an easy time estimating Jaccard similarity, because then we just have to see how many of the samples from the sample of the union that are in the intersection. And you can still do that using only the sketch from each set. You just have to do this intersection. So this is all easy to compute. It's not a problem. I'm just saying these sketches have a different nature than those we had before, where we just had this vector of k things. But it's totally doable, easy to implement, not a problem to code or anything like that. And then I have this theorem that, in fact, we have no problems, that the expected relative error is the same as the relative standard deviation we had with true randomness within a constant factor when we use this method. So we do know we have bias, because when k is equal to 1, which is an allowed special case, it's exactly the same as what we had before. So we still have the same bias. But the bias disappears together with the standard deviation at the same rate. So it doesn't hurt us, okay? And this was known to hold with 8 independents only for large k. But the really cool now is that this is the whole k independence paradigm. When first we have proved that something works with 2 independents, then we can use any 2 independent hashing, and we can wait for somebody to find a really fast one. And this is one that everybody should know, the one at Ditzfeldminger that just says, you want to hash a 32-bit number, you pick a random, 2 random 64-bit integers A and B, and you say A times X plus B, and you shift out the 32 smallest bits. You prove this works. It's not hard to prove, but this works, and it's blistering fast, because you're just paying for one 64-bit multiplication. Everything is kind of free. Else is kind of free, okay? So if that's all you need, and we've proved that in this particular case, then with the same data set as before, we get the convergence, but this time the convergence is to the right number. And it's actually also a much better convergence. It's a very sharp convergence. It's entered at the right point. And why is that? That's because we are using sampling without replacement, right? So we actually end up, at the end, when we have sampled all the elements, they're just there, and it's an exact answer. Okay, so again, I think this is a beautiful example. We have 2 schemes. When they're analyzed using full randomness, then they have exactly the same properties. They have the same expected error, which is 1 divided by the square root of the expected number of matches. So all the same, but when you plug in the nicest hash function that's known, I mean, this is the simplest hash function that has any nice mathematical properties. They're just not powerful enough for this scheme, but they are powerful enough for this one. It's the two independent. So we avoided the bias, and then the without replacement is also a win. And we're going to get back to that phenomenon. This is an extra gain we get from any of the things I'm talking about, which means even stronger concentration. So why does this work? So the proof is actually so simple. I'm going to mention to it because it's really so surprising nobody discovered it before. So the tricky point here is that the question whether X belongs in the bottom K depends on the hash values of all the other keys. So we have to deal with dependence. And to do that, we're actually going to do, the first thing here is ugly, so kind of forget about it for now. But we're going to define a threshold sampling probability that is completely deterministic, independent of all random choices, which is K divided by N, where N is the number of elements in X, and then also divided by 1 minus A. So if it's N divided by K divided by N, then I would expect to get K samples. And now I'll make it a little bit bigger. So I expect to, if I look at all the elements in the set X, I expect to get a little bit more than X elements out. Okay, so again, what I'm saying here is that I'm assuming that the hash values are uniform in 0, 1, roughly. Okay, so this being threshold sample. So we have the real bottom K sample that takes the K guys, which have the smallest hash values, but then I have a threshold sampling probability that's independent of what happens to everybody else, because we don't like dependence. So we just look at, you don't like the experiment, you just look at a different experiment and see if you can reason about that, and then you want to sort of move your analysis over to work for the case you're really dealing with. This looks kind of ugly, but essentially saying that if we have this oversampling, then either it's because we have sampled at most K, we have either threshold sampled at most K things from the big set, or the small set we're interested in, we've sampled too many of those. And it's by this factor 1 minus A or 1 plus A, and that's why it comes in here. So I will actually just move straight on. So if you don't remember what A is, it doesn't matter because it's written here. So if A is false, it's basically this thing that we had at least K samples, threshold samples from the set X. Now, S contained the K smallest set element. So that means that all of those guys got threshold sampled. Okay? So this is really extremely basic what I'm doing. So what does that mean? It means that everything we sampled from Y was also threshold sampled. And then if B is false, we said that not too many things from the subset we're interested in were threshold sampled, and then we just put the two things together. So all I just want to say here is that we had this problem of analyzing the dependence, and we avoided that by, instead of defining this artificial deterministic threshold sample that was a bit bigger than what we needed, we thought we needed to get K samples, and then we looked at the completely independent events instead. And then we can just apply Chebyshev to get bounds. Okay, but this also means that if we use something that's more than 2 independents, we get tighter concentration bounds, and then we get the same thing for the analysis of bottom K sketch. Okay, the rest is just calculations. But so again, I just want to say this is actually simple to prove, even if you didn't get it there. This was actually full detail. So I mean, it really isn't hard to prove at all. So both K-mins and bottom K, they generalize exactly the same idea of storing the smallest hash value. With limited independence, it makes a huge difference. To analyze it is really just the union bound in this case. And the other point here is that with simple hash functions, that's all you can do. The only thing you have is basically just union bounds, the narrative expectation, maybe a second moment bound, but that's really it, some variant stuff, right? But that's all you have. So you somehow have to be able to understand your problem that way, otherwise you can give up. And then it's also actually simpler to make fast because bottom K is just a priority queue. So you only pay log K per time. Every time an element comes, you have to see, does it have a hash value that belongs in the top K or actually the bottom K? If it does, you put it in. If not, you just skip it. Okay. So that's it. So in some sense, we would be done, but there are some reasons why I'm not so happy about the bottom K sketch. So before we saw that when we had to deal with the union, we first had to do some different operations to combine things before we could actually do some calculation. And this is going to be a problem. So I want to look at sketches that maps a set to a vector of K samples that preserve the similarity. So basically what I want is this thing we had with a broader scheme, which was, well, the whole idea that when I look at a coordinate, then the probability that I sample the same guy in that coordinate is exactly the Jaccard similarity. So I want to be able to look at one coordinate at a time and just get a good estimator. And then we, of course, just look at what is the fraction of matches we get to estimate the Jaccard similarity. And we want to have strong concentration. So this is all the things we had gotten from a broader scheme if we had truly random hashing, but I want to talk about it in a more general setting. And let me just say why this is important is because of this alignment property that when we can just look at the 8th coordinate, and that's in one set, and compare that with the ith coordinate in the second set, and that's the only relation we're interested in. There's nothing which goes across. When we did the bottom K, when we put the two things together, we actually don't know if somebody was the 5th guy in the bottom K sketch of one set should be compared with the 8th guy in the bottom K sketch, 8th guy in the bottom K of the other set. So there's no coordinate alignment. And one reason why we care about that is if we care about support vector machines, because then we want to do these dot products to see how much things look alike. Right, and then you can say, well, it's not really a dot product yet, but what you can do is that you can take your vector like this one, and then you can hash each of the samples into a bit string with only a single one, where the single position of a single one is sort of a hash value of the thing, and you combine it. I mean, the details are not so important, but just to say it's not too hard if you first have this kind of thing to convert it into something where you do have dot products. And one of the reasons why this is important is that when first you have these vectors, then you can subtract and add, and you could do this sort of combination of a lot of vectors. So at the end of the day, you can define a half space. So when you have your vector that represents your set, then you can just dot product with another vector, and if you get something positive, then you're in, and if you get something negative, you're out. Okay, but this really requires that you have the whole machinery of linear algebra at your hand for it to work. Okay, so this is why I claim we're not done just because we have a good solution for bottom K. That's why I want to have these vector samples where I have coordinate-wise comparison. And yeah, bottom K is hopeless in that. I mean, I actually have tried to see if we could somehow get it to work to simulate vectors, but I don't know how to define subtraction. I mean, that's the things that always go wrong when you have many. Okay. So what is it that's really happening? I'm just trying to step back and say, well, what is it that characterizes this sketch we get with Meanwise hashing? What we get is that if you have each coordinate is completely independent in this description, right? So we just look at some coordinate and we say, if the sample from a big set is in the small set, then you would sample the same element from the small set. That's also the basic consistency, and you get that automatically if you're looking at Meanwise hashing, because you take the guy with the smallest hash value. If you're smallest in the big set, you're certainly also going to be smallest in any subset. So that's all about basic consistency thing. And then we want this uniformity. That was a tough one, the one that said that each guy in a set had the same chance of being sampled. It's tough, but we're going to get it. Okay, but it's not going to be with the simple two independence. We need much more than that. So again, that's all you needed. If you had the consistency, then you have this property that the thing you sample from the two different sets is the same if and only if the sample from the union is an intersection. And then we have the Jaccard estimator. And it's unbiased if it has uniformity. Okay. So now we're going to discuss different ways of getting such a similarity sample, a vector. So not just a sketch, we actually want to get a vector. And again, sort of modeling using the same model, first we're going to analyze things assuming full randomness, and then afterwards we're going to see what happens when we put in a real hash function, which will be something I call mixed tabulation hashing. And the replacement, I will claim, works for lots of other things. So we're not just talking about similarity estimation, we're talking about counting distinct elements, flageolets, old papers, all kinds of different things will work using the same scheme. And then we'll do experiments and see the difference. So again, the scheme of Thorup, we've talked about it so many times. As a computer scientist, I always put everything upside down. So I have, in this case, 4 different columns, and I hashed them, and then the smallest one is on top, like with trees, they're always hanging down in computer science, right? So the smallest element is on top, and what we do is we took all these different elements, we sort of scrambled them in each column, and we just pick the top one in each coordinate. Okay, so we throw the elements from, we have k different bins, and in each bin we throw all the different elements in some random order and keep the top element. So our sample is just 5, 73, 52, and 73 because they were the numbers that were highest in each of these 4 different columns. And we have repetition, again, because each thing is done with replacement. Okay. And it's easy to see that it's consistent. This was the thing we talked about before. It's because when you sample the smallest element from a big set is also smallest in the subset, and uniform if we assume true randomness. And things are also nicely concentrated because we're just doing k samples without replacement. The reason why I don't like this scheme is that we have to run through our set k times. Right? We have k different hash functions, and we have to have our set. And then for each of these hash functions, we have to run through a whole set and see who has the smallest hash value. We're not assuming any relationship between the different hash functions, because then we have then the math is really gone. Okay, so the time it takes to compute it is the number of hash functions time the set size. And I'm going to show that we can actually reduce that. It was a paper together with some of my students at Fox, and we can actually get down to the set size plus the number of samples times log k. And Lee and some other people worked on this thing. This basic point is that k can be large. I mean, so this was a concrete case where I said it could be more than 1,000, but as a theoretician, it's kind of clear it could be large. You want to have an error epsilon. Then the number of samples you need is proportional to log n divided by 1 over epsilon squared if you want to avoid n bad events, which we typically, if you have n sample points, something like that. Right? So if you want a 1% error, then you're talking about log n times 10,000. And so that's going to be 1,000,000. So just to say, it's very easy to see that this number of samples you want is very large, say 10,000, and multiplying that with a large set is it just sucks. So we would like to save this factor 10,000. If the different hash functions were sufficiently related, then we could do something more efficient. Barros and Porat has studied if they're pairwise, but then we're never going to get any concentration bounds that are better than Chebyshev. We're never going to get Chernoff or anything like that. So that's useless for statistics. So then there's a completely different scheme or a different idea. It's very cool. It's by Lee and some co-authors. And they say, instead of throwing, so what we had at the moment was we had k different independent experiments, and in each of them we use the hash function to scramble the numbers and see who's smallest. Instead, what we now do is we take every single key and throw it in a random bucket out of k, and it gets some hash values. So now for each bucket, we only take the smallest element. Okay. So now for each key, we only have to compute 2 hash functions. One that tells which bucket it belongs in, and what's its hash value. So now we just do 2 things instead of 10,000 things for each key. So now each key appears only once in these k buckets. And for each bucket, we take the smallest one, which is the one on top. So 99, 52, and 73 are the ones on top. And we have only one issue here. There's nobody landed in this bucket, so it's empty. But otherwise, we have something that's extremely much faster than what we had before. Okay. And the computation time is clearly linear in the sketch. You can even have these things being implicit, so it doesn't matter how many samples you want. You're never going to spend more time than proportional to the set size. Okay. But if we are so lucky that the set is large, much larger than these 10,000 we had, more than k log k, so more than 1 million or whatever it is, then with high probability we get balls in every bucket, and we take the top ball or the bottom ball in every pocket. So this gives us k samples without replacement. And generally, without replacement is much better than with replacement. That's the same thing as we saw with bottom k. Okay, the bottom k sample was also without replacement, so is this thing here. Okay, and it's consistent, it's uniform, everything is perfect, if we make this assumption. But the undesigned samples pose some problems. I mean, the dot product doesn't make sense anymore. It doesn't really work. I mean, again, the reason why we didn't just want the vector thing was because we wanted to have these nice defined dot products. And if you imagine you're sort of building this system of all these sketches, and then you discover, wait a second, we can't have sketches that are this big because now some idiot came with a small set, and we had forgotten to say we're not allowing small sets in our database or whatever it is. It's better to have something that always works and always works well. So he became aware of that together with different people. They wrote a lot of papers and had all different variants for how to fix the problem. And the sort of the simplest one, the first one was just, how about just copying from the left? If you're empty, you just take the answer from the left. And the truth is this, in some sense, works for some of the things. It's still consistent. It's going to do the right thing, but you are not, I mean, here it doesn't matter so much. You only had one missing space, but you're not getting extra information. You still have only the same information as you got in the first round. So if you have some empty buckets, they're lost. So the concentration is no longer exponential in the number of samples, right? The whole reason why we do many samples is because we want to claim exponential concentration in the number of samples. And this thing here screws that. So forget about it. It looks complicated, so let's skip it. So what we suggested was, instead of copying, we just keep doing rounds of one permutation. So one permutation is just this thing that throws every ball into a bucket somewhere in the bucket and find the top guy in each bucket that got filled. So here we got these things filled, this thing did not get filled. We just run it again. Okay. But we only use it to fill positions that we didn't fill in the first round. So in the next round, we get 52, 99, and 73. 73 and 52 are useless because we already got something better, but this one is good. We do this for k rounds. And at the end, we do k-mins, which was this original scheme of Broder and those guys, which just says, for every single coordinate, we throw all the balls in there and take the top guy. So for sure, we got all positions filled because the last round is going to fill all positions. Of course, this looks like a very slow scheme because we're not just doing k-means, we're doing k-means plus k1 permutation. So this looks bad, except we can stop here, right? So as soon as all the buckets are full, we can stop. We don't need to do any more. Okay. So before I talk about speed, let me just say that look at the difference it made. So here's the real min hash, and I've used something that is like fully random. I used 100 independent hashing, so a degree 100 polynomial, and just pretended that's good enough. And we get these nice normal distribution with min hash. Then comes these different copying schemes that Lee suggested, where we copy from the left or copy from random. And then comes our paper here. And what is special about when we use this copying is that we get these zeros that we shouldn't have gotten. And why is that? Well, I'm dealing with, as a typical mathematician, I'm dealing with very simple sets. One set is 1 and 2, the other is 2 and 3. Intersection is 2. We have 3 elements in the union. But what goes bad in the first round is that if 2 ends up below 1 or 3, right? So in this one permutation hashing, if you end up below in the first round, you're gone. What Ping did was, he would just copy from other places, but 5 is gone forever if you just start copying, right? So then you have 0 intersection. So that's exactly the phenomenon we see here. And also you just see we get much stronger concentration this way. I mean, it's pretty obvious from the picture. And I also claim it's fast. It only takes k log k times with high probability. Why is that? Right, each round we're throwing A balls into K bins, and that takes A time, okay? But all bins are full when we have thrown K log K balls, so each round throws only these A balls. So I would be, if we have enough balls, we're done in the first round just with one permutation hashing. We may have to continue some more, but we know how many balls it takes to fill everything assuming full randomness. And this K-mins we only do at the end. But if we do it, we've already spent K rounds to one permutation hashing, so that could only double the total time. So again, we're basically just looking at how long time does it take to fill all the bins. The last thing is just a hack to make sure we never lose more than what corresponds to at most K rounds. Okay.
Is it important, like, if it happens with so low probability, isn't the case that whatever you do in the last step, it wouldn't matter?
Well, so yes, I just like that the system is always well defined. I prefer that the error probability is in the time rather than in the correctness, right? So we have a system which is ill-defined if we are missing something. I don't like that. So I also like that I can promise that so this scheme has a worst case time of k squared. I could also it's just a choice. I could just have continued with one permutation hashing until everything was filled, then it would still be well defined. But I kind of like that I both have a worst case of k squared. This gives sort of the best of all worlds. That's the only reason. It gives the nicest theorem. So it's always correct. It's only the time, the running time is high probability, and it cannot get above k squared. So it's just a choice. But it's easy to implement. It doesn't make any difference. So what I find here is interesting is whole sort of comparison of with and without replacement. So we have a perfect implementation of sampling without replacement, except it takes a long time because you just do k independent rounds and you pay linear time in the set size for every round. Then we have the other extreme, which is one permutation hashing, which is sampling without replacement. And it clearly takes only set size time, but if you say imagine that the set is smaller than the number of samples, then for sure we're not going to fill all the slots. So you're going to have problems with that. And then we have this thing here, which is sort of a funny combination of with and without replacement, because in each round you get a bunch of samples without replacement, but then you restart completely independently and put in a new round and continue that way. And then everything is with replacement. But the cool thing is really fast, right? So if you have situations where you don't really are strict about whether it should be with or without replacement, then you have a very fast option. And for example, this thing, you get exactly the same Chernoff bounds as you get if you have full randomness. So because what basically happens if you derive these Chernoff bounds using the Taylor expansion, then you'll see that you can only decrease moments. So everything can only get better. And that's also what we saw when we ran the experiments. Everything was actually better concentrated than if you did things with replacement.
Actually, you should even get something better, perhaps.
Yeah, I'm saying it's better. It depends. But since we're not promising that we have, it could all be with replacement. So we can't promise that, right? So it can never get worse. It can only get better. And that's sort of nice. So, but we have no old notation hidden or anything like that. Things are at least as good as with a replacement. Okay. So now I will talk about, can we implement this thing? And we already had the problem with this bias stuff. We have to fix that. And for now, I just assume that the problem is not getting the thing filled. So let's just say the set size is big enough that all the things get filled. So I just want to look at the one permutation hashing case. What I'm presenting for you works for the whole thing, but I don't want to deal with the details. So again, we just assume we are in this world here where the first round fixed everything. Okay, good. So I'm going to talk about red and blue balls, and the blue B is not the same as original B. Just to say I'm going to misuse this thing, but I like just R for red and B for blue. So forget about that. As I said before, we're really just talking about, yeah. Okay, so we have red and blue balls. And we're going to try to estimate the number of red balls amongst these balls. So we want to make a vector of k samples from the red and blue balls. And we want this nice concentration that the number of samples, the number of red samples is what it should be. And I'm first going to, so the generic way of implementing such a scheme is that you take your keys and you throw them into L bits, and you use the first log K bits to tell you which bucket you want to end in, and then you use the remaining bits to have this local hash value that you use to find out who's biggest and who's smallest within each bucket. That's just one of the many ways you can do it, but it's at least a natural one. So again, I'm going to look at the same example. We're going to just, so we're basically just computing one hash value to get both of these things, the bucket and the local hash value. And I'm going to see what happens if we throw a very simple into the classic textbook hash function, a times x plus b mod p. The same thing if you use this one of developing, but this is a little simpler to work with. And if it's fast, it's a Mersenne prime, but that doesn't really matter. But we have L bits, and we're going to use the first of them for the bucket and the last for the ordering. And then we're going to look at the example I mentioned before. The blue balls are just 1 through 25, and the red balls are random. We're going to look at where they hash. And now if I can find where it starts. So assume B is such that the first place we hash to is here. So that's one hash here. Then we are adding the A. So we go somewhere here. Then we add A, we go here, here, here. And we keep going systematic like this. Every time we add A, it's the same amount we move in the circle. Right? Because this is again mod P. This is a mod P circle, so this is a value of P minus 1. Right? And so every time we add 1 to the key value, we add A to the hash value. It's always going to move like that. It's completely systematic. So this is how this is going to hash. And the red guys, because they're random numbers, they're just going to be random places. Right? And what we saw here was that even if we had lots of balls, we actually didn't fill one of the buckets because things are completely systematic, right? We just get the same sequence of concentrated sequence copied several times. And we can see who wins in each bucket. So red won in the first one, then blue won here, red wins here, blue wins here, blue wins here, blue wins here, red wins here. It's all alone, even though it has a really poor position. And again, blue wins. Red wins way too often, right? Because the blue guys all got concentrated and got it repeated everywhere. So they really don't have much of a chance of winning. In some sense, only get 1, 2, 3, 4, 5 chances, even though there are 25 of them. Okay. And so the most important thing is there's no independence. I mean, all the buckets kind of look the same. You have this dense segments of blue and then a red somewhere. Okay, so everything we hope for concentration bounds, we can forget about it. So we somehow need more independence between the buckets, right? We're throwing balls into K buckets and we pick a random element. We're doing the sampling. And again, we want to have this full randomness with concentration bounds. But we want something that's implementable. And somehow this requires a lot of independence between the buckets. And I want to talk about it more generally because, I mean, this is a very generic issue. You want to throw balls into bins, and you want to do a statistics on each bin, and then we want to be able to aggregate these statistics and get concentration as if it was independent. So that's the same thing as Fletcher did many, many years earlier to count the number of distinct elements. He basically said, who is smallest in each bucket? Looked at that value, and then he did a very complicated function and used that to make a conclusion. But the generic thing is just, you want to have K independent experiments, but that's way too expensive. Instead, you throw things into K buckets, get some conclusion for each bucket, and pretend that these are independent experiments and get something that's as good as if it was. But you've got everything for the price of one hash function. Okay, so we save this factor 10,000 at speed or whatever it is, and it's a true saving, right? I mean, the code is not more complicated. You just compute 2 hash functions instead of 1. So you're really having this big saving on dealing with your large data sets. Okay, so how can we do that? So I'm going to use something that I call mixed tabulation hashing. And even to describe it, I have to first talk about simple tabulation and then apply it. but it's a very generic method that I will hope to convey to you. So simple tabulation is something that goes back to chess computers. I've talked about it before here at Google. You just have your key and you divide it into characters. So think of it as 4 characters, but it's a 32-bit key, but it could also be 16-bit characters. And then you have a truly random hash function for each character position, but it only has to map characters. So only 256 characters to map. So we don't have these space problems we had if we tried to make tabulate the hash values for every key in the universe. It's only characters. And then the hash value is just the XOR of the hash of each key. So it's very simple to implement. It works in cache, hopefully, and the running time is basically just doing these XORs. And just to say, at least in the experiments I ran, this was as fast as 2 multiplications. It's something you can actually code easily. And one thing I want to note about this hash function, one nice feature that we're going to need is that every output bit is completely independent. Because if you look at the 7th bit in the output, it's just the 7th bit from each character table. And since the bit in the character tables are completely independent, they're fully random, there's no relation. So if you don't have any information about the 7th bit, it doesn't tell you anything about the 20th bit. And one of the old theorems approved with Petrasco many years back was that if you use this kind of scheme to throw balls into bins, then you get Chernoff style bounds. So at least if you know these Chernoff bounds, we know about how many balls thrown into a bin, we see how much it deviates from the mean by some delta, then you get this Chernoff style bounds, except that there's an omega, which means that the decay is slower by a constant factor. And you also have this higher order probability bound. I mean, with what high probability things work. Okay. And again, with the bins, we can look at any bits. So now comes the mixed tabulation hash function. You just do it twice. So first you use a simple tabulation hash function you want to just define to take your C character input and get a D character output. And then you have a new hash function, also simple tabulation, that takes both the original characters and the D new characters. Okay, so it's just in the form. So the second hash function is applied to the concatenation of your first hash function and the output of the original key and the output of the first hash function on the original key. So you kind of have both the original key and some scrambled characters. We're sort of putting some more randomness into the system, but it's not worse than that. And then comes a crazy theorem. It says, look at any subset of the bits in the output and use those to define a set C. So you take your key. The only way you're allowed to select elements is if you look at the output in these deselected bits and the original key, nothing else. And if the expected number of things you sample that way is less than the alphabet size divided by 2, then with high probability, all the other bits are completely random. So one extreme example of that is that if you look at nothing in the output, so you basically just look at a set. So we're allowed to look at the set and say, well, we like those guys. If the set is smaller than the alphabet size, then it's just any small factor, then you have a completely random hash function on that set. So this is much simpler than any previous construction of that, and that's very useful, right? So it basically says, so how much randomness do we have in the system? We have a totally random table over the alphabet different keys. We have C of those, but that's basically the total randomness in the system. And now we say, if your set is just a little bit smaller than the total randomness in the system, then with the high probability, you have a totally random hash function in that set. So for many different applications, that's all you need because you're never going to work with more elements than that. And then with high probability, things are totally random. So any theorem you have proved assuming true randomness will work directly. Okay. So we have this theorem with this corollary I just mentioned. Okay. And I said this is simpler than anything that was known. And I just want to say the code of this thing, I mean, just to say it may look ugly, but it's something you can implement. This is a full C code of this thing. So it's something you can actually run and it works very fast. It's almost as fast as simple tabulation. And so we had this basic theorem. So when I want to apply this in the context of vector sampling, I'm going to pick, so sigma was sort of the size of the alphabet. That's how much randomness I'm willing to put in the system, how much space I'm willing to use. I'm going to make that a log factor bigger than the number of samples I want. When I sample from these disjoint sets A and B, so red and blue, there are no purple balls. Everything is either red and blue. Okay. So if the total number of balls was actually smaller than sigma half, the alphabet size half, then we have full randomness, and that means analysis we did is already perfect. There's nothing to prove. Okay. If it's bigger, then we are in the one permutation hashing case. So in fact, I'm claiming the situation where one permutation hashing works. Our simple mixed tabulation works directly with high probability, no problem at all. We don't have to prove anything. So now we just focus on this case where the number of balls is much bigger than the randomness sigma in the system, or as big. Okay. So that's the case we're focusing on, and we're still having this scheme where we just throw each balls in the different bins and we pick the one with the smallest hash value. So what we're going to do is that we're going to look at some of the set most significant bits, and we want them to be zero. So again, this is a local hash value, the one that decided you're ordering within the local bin that you landed in. And the smaller you are, the better your chance of winning. So we're looking at guys that have set zeros, where this is designed so that that means that the probability that a ball have that many zeros is basically this k log k divided by the number of balls. So we basically expect some balls to have that many leading zeros. More precisely, in each bucket, the number of balls that have that many zeros, leading zeros, is going to be log k. And then we have the usual Chernoff bounds that say with high probability we get such a ball. So we're basically just saying we're asking for so many zeros that we are, with high probability, every bin has a ball with that many zeros. So it means that all the things we sample have that many zeros, that many leading zeros. We're just deciding that number of zeros. Okay, so again, the more leading zeros you have, the smaller you are. And we're just finding a threshold for small, translated into a certain number of leading zeros that is such that every bin has a ball with that many zeros, with high probability. So all the samples would have set leading zeros. Okay, and now we just pretend that there's the same number of red and blue balls. And now we just look at the red balls that have these set leading zeros. So that's just what we think of as small, right? So define the measure of small, which is so that all the bins will have a small ball. And now we just look at the small red balls. We still don't know if they're going to win or not. But so now comes, we're sort of looking at things in two different ways. Now we look at the expected number of small red balls. So there's going to be, each bin was supposed to have log k in expectation. So that means the total number of small red balls is k log k. And now the important thing is we don't care which bin they land in. We just notice that the expected number of red balls is k log k. But this means that the concentration of the number of red balls is like something with k log k samples. Then the error we get is basically 1 plus minus order, and then 1 divided by the square root of the expected number of balls we got. So it's a comparatively small error, right? So this error is basically with high probability 1 divided by square root k. Okay, so the difference I just want to emphasize is if we now look at the number of red balls in a given bin, it's only log k. But we're not happy with the deviation in that because that's a small number. So deviation in how many red balls we get in a given bin is there's a lot of deviation there. But now we're looking at the union of all the red balls and see how many small balls we get there. And because that's k log k, then with high probability, the deviation in the number of small red balls we get is very small. And that's just using simple tabulation Chernoff bound. Okay, so we have a very nice concentration number of red balls, small red balls. It's just about exactly what it should have been. And the same with the blue balls. So we have roughly the right number of small red balls, roughly the right number of blue balls, and they all have the same probability of being that. So this means that if we look at the ratio between small red balls and red blue balls, it's the same as the ratio between red balls and blue balls. And the total number of small balls is the alphabet size divided by 2. That means that everything else is totally random. Okay, so we know all our samples are small. We know we have almost exactly the right number of small red and this small blue. And we have an experiment that's fully random when you restrict it to small balls. So this means that we're actually just doing a fully random K sample without replacement on the small red balls and blue balls. And then we have the classic Chernoff bounds that you can apply directly, which just says now you get a good concentration on that. Okay, so the nice thing is that the error we got from the restriction to red or blue balls, to small balls, is much smaller than the error you get in the end. So the way we handled this thing was we viewed it as being a two-step thing. Right? We wanted to convert to the case where we conclude we have full randomness. If we start off with way too many balls, it could be much bigger than K. But because we are only going to do K samples in the end of the day, we don't even want to benefit if it was many more balls in the universe. We don't care. We just define what is a small ball. Where small ball, there are enough small balls that we're sure that all the samples are going to be small. We have more than K of them, K log K of them. We get a nice concentration when we do the restriction. And now we just have fully random samples where we can use all the basic math we know fully about random samples to see how big the deviation bounds. So that means that the errors we get are just a little low compared with the errors we got compared with the results with full randomness. And this technique is completely general. That's why the same technique also works for counting distinct elements and stuff like that. Everything works. So this is sort of the whole goal here was we wanted to have what was like if we had K independent experiments. And we saw using this mixed simple tabulation Chernoff bounds that we managed to just mess up the experiment a little bit before we got the full independence. So I'm not going to look at the other case, but this can be used fairly generically. So what I just want to say about these results is that I wish I had something like the independence paradigm. It's so beautiful. You just say, you look at the independence, it's K, and then you have K moments and stuff like that. The math is really simple. But here, to get this thing to work, to get all these things, to understand all these things, the only thing I used was this very powerful theorem that says you can look at some of your output bits, and if restricting them, by looking at them, you can select something which is smaller than the amount of randomness in the system, then you have full randomness at the whole thing. Also use these kind of methods, they give Chernoff bounds, but that's again something we know how to use. When we design algorithms, we use Chernoff bounds all the time, and we get those within a constant factor. So that's sort of a standard thing to use. And I used that these output bits were independent. But that's all I needed to prove in a sort of fairly black box way to prove anything. I didn't have to understand the full complexity of simple tabulation, which is really hard. Then you'd have to read what you call 30 pages. So that's pretty quotable lemmas, theorems that you can use to reason about these things. Does it work? Well, so first, I think the interesting thing here is we compared the speed against our thing with different things. So this is a mixed tabulation down here. You will look at these multiply shift, 2-wise polynomial, 3-wise polynomial, and we see we're sort of as fast as at least 3-wise polynomial hashing. Three independent hashes. So that's like a degree 2 polynomial. Okay, so we are sort of at the speed of 2 multiplications. The other alternative that people often mention is crypto functions. They say some smart people think that this is as good as random, so let's try it. And of course, then they say if it doesn't work, you'll get rich because you have found a counterexample of some crypto thing. Well, so in fact, we already know that murmur hash doesn't really work, but at least it's fast. And also, would you get famous? If you use this thing for estimates, you don't find out if it's wrong, the estimate, right? I mean, because you don't have the real data. If you use this thing, I mean, as an ATT for traffic measurements and use it to decide where do we need to add more capacity in the network, well, you may discover that you added the capacity and it didn't help you. But that doesn't allow you to conclude that the data was wrong and get a crypto price because you now have a counterexample. They wouldn't buy that at all, right? I mean, because they'll just say it was the traffic that changed. So there's normally no way of going back and finding out that the crypto thing didn't work. So you're just crossing your fingers, that's all you're doing. These are the crypto functions I think people trust more, especially Blake 2, but you see it's not very fast. So what we get down here with this thing is something that provably always works. It gives good probabilistic properties for every input. Of course, it's probabilistic functions, so of course it doesn't always work, but there's no input that can make it screw up. And it's actually faster, at least as fast as these crypto things. So you no longer need to cross your fingers, you just use one scheme that works. Can we see it works? Well, so here we have these different, what was this thing? It was just where we saw how much the vectors had the right similarity and we looked at the errors. But these are the simple methods. You can see they're not normally distributed. Our thing is normally distributed. We can't distinguish it between murmur hash and random. Our advantage is that we know it works and it's fast. So we have a proof that the picture will always look like that. I kind of forgot exactly what this is, but this is inside locality sensitive hashing. And if you're to the left, it's a good thing. And this makes tabulation compared with these multiply shift or primality thing. And at least if you believe me, that's good to be to the left, and you can see the green is better than the blue. And we're kind of surprised that in something as complicated as locality sensitive hashing, where you're not just first doing the similarity right, and then you're doing all these tables, you can actually see a very marked difference whether you use a good or bad hash function. And these are, again, from real data sets, standard collection, handwritten digits, something with newsgroup documents. So this was not like the experiments which I said before, we had the number 1 through 25 and some random ones. These are from real data set. And there was, as I say, an earlier machine learning paper that claimed that things were always the same. But when first you know where the hard examples is, it's very easy to find real world examples that screw up the outcomes when they use the wrong hash functions. And these were, well, some other things. We also looked at feature hashing, which is something that's also popular in machine learning, where you just take each vector and map it to a random vector with a plus minus sign, and then you see how much things compare. And again, we sort of see, especially here, a big difference whether you use the good hash functions or the bad hash functions in the concentration. So just concluding remarks. It has been a long talk, I'm sorry. We looked at first the k-means versus bottom k, which I think was the most beautiful example of the difference it makes whether you use a good hash function or a bad hash function. And the bottom k also had this advantage of being without replacement. We have seen the advantage of that several places in this talk. It's also very efficient. We weren't totally happy with it. Doesn't solve everything because it can't be used in these support vector machines. It can't be used for vector situations. It's not a linear sketch. It has all kinds of caveats to it. So that's why we would like to get these vector hashings instead. And for vector hashing, we actually have a scheme that, well, we saw both that it works experimentally, but also it provably always works. It's actually at least as good as with replacements, provably in connection with Chernoff bounds and everything like that. And it's very efficient because we can stop as soon as we found all the samples we wanted. We just did one permutation round until everything was full. So you get this, instead of paying the set size times k, you pay the set size plus k log k. Sorry, what's happening here? Okay. And that was all very good, but it was still assuming full randomness. So now we try to see what happens when you throw in a real hash function. That the challenge you have is you want to throw balls into bins, and you want to collect these statistics from different bins, and you want the statistics to be pretty independent. How can you do that? And then we use this mixed tabulation, and that was basically the answer we got. We got you could see the difference in these real data. And the nice thing is it's faster than crypto things, and it always works. And we can promise that because it's mathematical. Open problems, use tabulation hashing to solve everything. I'm still working on that. I think it's very mathematically challenging, interesting problem is to try to replace the XOR with the multiplication. Because then what you're really doing is that you're finding a replacement of Norton-Neeson's pseudo-random number generator. And there's a chance that can do amazing things. So the theorem I would really like to see is a theorem that says this thing, if you're doing any sketch that only looks at B bits from each bin, so you have these K bins, right? And I would like to have a theorem of the type that if you just look, if you're generating with any computable method you can imagine, a sketch consisting of K bits, or B bits from each bin, and then you do any aggregation you want of that stuff, something like that, then no computation without a lot of space would be able to distinguish what you have done from true randomness. Okay, so this would be the completely, I'm just saying that's a statement of a similar type of what Norton-Neeson's thing, right? So at the moment we saw one sketch which was based on what's the smallest hash value you've seen in each bin, or in our case, is it red or blue? That's just one bit. So that's, I mean, this is the fundamental nature of what is a statistics. A statistics is something with few bits. So if we could get a general theory that only use that you are not allowed to look at more than a few bits based on the bucket, then we should be done. So I think that works, but I can't prove it. But that's the most general thing you could possibly imagine. So that's it.